Okay, so question 9A through 9F. So this is one of the applied questions for Chapter 3 from An Introduction to Statistical Learning, second edition. This video is in R code, and I will make a separate video for Python code. So here are the questions, and I won't read them all right now, but we are running linear regression, similar to what we did in number 8, in question 8. But in question 8, we regressed on a single predictor variable, and now we are using multiple linear regression. Okay, so we're going to consider all except for one predictor variable. Okay, and then we're going to do some things with the output. So the first thing that we need to do is to install and load the ISLR package in R and pull up the auto dataset, which is part of the ISLR dataset. Okay, I've already done this. And so question 1 asks us to produce a scatterplot matrix, so many different plots will be included here for all variables in the dataset. Okay, and so so the command for that is just pairs. Okay, and so I can pull that up, and that's very small. So if I open that in a new window, this is what we get. Okay, so so we have the variables here along the diagonal, and so if I want to look at relationships between any two variables, let's say miles per gallon and weight, I simply go over and up from weight, and so that's the scatter plot for those two variables. Okay. Similarly, I can go from weight and go the row of weight and go to the column of miles per gallon, and this are the same. Okay. Just because we drop this variable later, and I think that it probably makes sense because it makes sense, I am going to drop one of these variables. So I'm going to subset my data, and I'm just going to select a set of these variables, and actually I'm going to deselect the variable called name. Okay, so let's run that, and this will make the image a little bit bigger. Okay, so I've dropped the name variable, and these are a little bit bigger now because of that. Anyway, same idea. Okay. I'm also not sure what origin is. I should look that up, but that doesn't seem to be very important. But anyway. Okay. So for part B, we want to compute a correlation matrix. Okay, excluding name, the variable name. Okay. So all I'm going to do is I have core, and I'm subsetting my data, and I'm wrapping this all in a round function. Otherwise, we get 10 decimal digits, which is ugly to look at. But anyway, so this is our correlation matrix. So similar to the pairs plot up there, if I want to know the correlation between any two variables, I find it in the row, and I find the other one as a column. Okay, so if I want miles per gallon and horsepower, this is the correlation between miles per gallon and horsepower. Okay. Notice that there's ones all down the diagonal because that is the correlation with each variable with itself. So miles per gallon is 100% correlated with itself, so on and so forth. And then there's one more thing that I want to mention here, and that is that when we run the multiple regression, we will get estimates for how each of these variables relates to miles per gallon. Okay. And now you might think then that the estimate for cylinders with miles per gallon might be this value, and for displacement would be this value, and that would be incorrect. So these are correlations, and the beta coefficients in the regression are more like partial correlations. What's the difference? In the correlation matrix, well, actually, let me back that up. In the regression, the values, the estimate of the relationship has considered the relationship among all of the variables included in the regression. This correlation matrix does not. So for instance, the negative 0.78 does not take into account how all of the other variables are related to each other as well as miles per gallon. So anyway, okay. So now on to C. So we're going to do multiple regression here and summarize the output and kind of talk about the output. All right. So we have the LM function again, as we already saw, and I'm regressing miles per gallon on. And when you have this period here, it is regressing on every other variable in the data set. Okay, and what is our data set? Well, it's the auto data set, but I am again removing name. Okay, with that same subset trick. So all of the variables in our data is all of the variables in auto minus the name variable. Okay, so all right. So we are specifically asked here whether or not there was a relationship, or if there's relationships between the predictors and the response, and which predictors have a statistically significant relationship, and what does the coefficient for year suggest. Okay, so I'm going to take these one at a time. So first of all, I don't like the idea of saying, oh, this one has a relationship and this one doesn't, okay? The estimate is our best estimate of the relationship between the two variables, and only a value of 0.0000000 would mean no relationship. These are our best estimates of the relationship, okay? It is a separate question then to ask, how much confidence do we have in our estimates of those relationships? And that confidence is summarized, or often summarized, or partially summarized in our p-values, okay? So for instance, if I go to, let's find a decent example here. So if I say, what is the relationship between acceleration and miles per gallon? I'll say, well, my estimate is that as acceleration goes up, miles per gallon goes up like this. But I'm not really confident in that estimate. Okay, so that's how we probably should think about those things. One more point here is that our confidence, these p-values, are only good insofar as we trust the assumptions that are embedded in this model. Okay, and so even our confidence is contingent on other assumptions that are not found in the data. Anyway, so now we're asked specifically to look at year. So how would I interpret the information for year here? Well, so we see a positive coefficient, okay, and a very low p-value. So what this means is that as year goes up, so newer cars, gas mileage goes up. So newer cars have better gas mileage. And specifically for every year newer, if that makes sense, that a car is, we should expect to get 0.75 more miles per gallon. And the very low p-value suggests that we should be pretty confident in that estimate given the assumptions that are embedded in the model. Okay. So now for D, we are looking at some diagnostic plots. Okay, and so we saw this in the last video, and we get the exact same plots, but now whenever we see something like fitted values, we have fitted it to multiple variables. Okay, so the fitted values have now accounted for multiple variables. All right. And so we're going to go through and just kind of maybe give an opinion of the fit here. Okay, so in the residuals versus fitted, I noticed the same thing that I saw in question 8, which is it seems to be the variance seems to be a little bit inconsistent as I move from left to right, which is heteroscedasticity. I can't say it. But that's violating one of the assumptions of normal linear regression. I also see that so now my QQ plot is helping me to determine if a normal distribution was a good fit or a good assumption for the distribution of my data, or specifically the residuals of my data. And again, we see that there's quite a bit of deviation, so maybe not. The third plot, I don't usually get a lot of use out of the third plot. I more or less get similar information from the residuals versus fitted. But anyway, And the leverage, leverage versus residuals, I see that there's a couple of high leverage points. Okay, maybe this one, certainly this one, and so the threat of high leverage points is that they may exert undue influence over the fit of the regression line. But in order for that to happen, they must additionally have a fairly high residual. I'm not really sure that this qualifies as a very high residual. It seems to be a little bit less than 2, and so maybe it does. But it may be an outlier. It may be something we need to check in the data. But anyway, so all in all, I would say that our model is not doing a great job of fitting the data, but certainly it's doing better than when it was just a single variable. Okay. So in part E, we want to incorporate some interactions. So, and there's 2 ways to specify interactions. One is with an asterisk, and the other is with a colon. Okay. And the difference is that when I use an asterisk, so for A and B, I get the interaction between A and B as well as the main effects of A and B. And then, but when I use a colon, I just get the interaction between A and B. And so I've done that here. I'm running a little bit low on time here, and so I'll just trust you to go through and look at which ones have asterisks versus a colon, and how that plays out here in the output. Okay. Okay. Finally, for F, we want to transform the x variable, which in different ways, using x squared, log of x, square root of x, and just look at maybe some of the consequences of that. And so what I am going to do here is I'm going to take the regression from number 8 that just has a single variable and transform that variables in different ways. So this is the original regression where horsepower is not transformed, and then I log transform it, and then I square root transform it, and now I square it here. And when we're going to square something like this, we need to put this little I out front, which I think means identity. It's because the caret has another use in the LM function, so it's just something you do when you need to raise something to a power. Okay, but anyway, the results here are not ground shaking. Obviously, whenever we are transforming the x variable, we're inputting different data to the regression, right? And so here I have my 4 intercepts and my 4 beta coefficients for the different transformations, and of course they're all different, and you wouldn't expect anything else. I don't really know what to specify as far as being different because everything's different. We've used essentially different data here. Another way that we could go about this is we could plot these diagnostic plots, and I'm just selecting certain ones here. And so I could go to here to kind of blow it up. But these are a few of the diagnostic plots. Again, you can go through and pick out however many differences you want here. But of course, that's completely expected because we've regressed on completely different data in each case. Now, if I was trying to determine which ones I like, or which of the transformations I like better, then I may use these plots to say, to do things such as look for, to see if maybe the QQ residuals fall more on a straight line, right? Indicating a better approximation to normalcy, right? Some of these transformations help to normalize the residuals. I may look for one that removes outliers, right? Not because, well, by doing something that removes the outliers, that means that my model that the assumptions of my model are less likely to be violated, and so on and so forth. But running low on time, so I will call it good here.